Given the high-level language, we have several different approaches about how to execute a high-level language statement. So you could write in Python, or you could write in Java, or you could write in C. And there's two different basic approaches to running those programs on the machine, sitting at your desk at home. And the first is interpretation, and in some ways it's the simpler of the two approaches, because you have some hardware that you're running, in this case, say a beta, a little hardware interpreter. It reads in those 32-bit binary numbers and executes the instructions one by one. Instead, what we'll do, and so you could say, look, I could write it in assembly language, but that seems very tedious. So what I'm going to do instead is to spend some time and write a program, which is called the interpreter, which I'm going to use as, if you will, another level of machine. So there's this notion of a Python machine, and the Python machine has Pythonic operations. You can use, tuples and lists and dictionaries and things like that. So this machine has a much more interesting repertoire than just 32-bit binary numbers. And it provides for all sorts of exotic control structures and threads and neat things like that. And then what I'll do is to I'll write in a high-level language that's meant to be executed by this really nice machine, M2, and then I'll write a program in M1's language that interprets M2 programs. And by interpret, what I mean is that it doesn't do a permanent translation from M2 to M1. What it does is that it takes a representation of the M2 program and then just sort of looks down and does each statement one at a time while the program is running. There's no permanent translation that goes on. That'll come up in the next thing. So we have this sort of notion of a hardware, an x86 or a beta hardware, on top of which we might, for instance, write a Python interpreter, and then we would write my application in Python code, and the interpreter would basically look at a representation of my application and choose to sort of walk around the representation doing whatever it says. No permanent translation, but just sort of on the fly interpret my Python code sort of statement by statement, and if there's a loop, it'll go back and start reinterpreting the statements at the top of the loop. And of course, on top of that, my application may in fact be interpreting, data or something like that. So that's sort of what interpretation is going to do. An easy way for us to write in a high-level language, but through all the hard work here of the Python interpreter, actually execute it on a machine like the x86 or the beta. Compilation is actually, it does much the same thing, except it involves a permanent translation of the original program, a Python program or a C program or a Java program, into a separate new program. And the idea is that this translation preserves all the semantics. It figures out how to use the low-level details. If I have a list, how is that actually represented in memory? And if I access the 17th element of the list, what does that actually mean in terms of beta instructions? It figures that out all at once. At compile time, it does it once, and then when you actually run the program, there's no reference back to P2. The program is actually just a sequence of assembly language statements that the hardware interpreter runs. So this notion of this sort of one-shot translation, this program we call a compiler, does that translation once, and then the program you run is the so-called compiled program, or in this case it's usually a representation of the actual assembly language instructions, which then get executed. Okay, so why do we choose compilation versus interpretation? And it has a lot to do with just sort of what is easier at the moment. Typically, running interpreted programs involves sort of less steps. You don't have to go through a compilation step. And so you tend to sort of, you can use interpreting programs like Ruby or Java, or Java is somewhere in between, but Ruby or Python or something like that, JavaScript. You can pound out the code and you can run instantly. There's no, so I have to go run the compiler and then take the output of the compiler and load it onto the machine. So interpreters are sort of more agile, but they often pay a bit of a performance penalty because there's this layer of interpretation that's going on, as opposed to directly translating the program into machine language statements. So here you get sort of a sense of, if I type in x plus 2 in a program, an interpreter would actually say, okay, I'm going to look at, get the value of x, and I'm going to get and add 2 to it, and it sort of every time it ran across that statement, it would do the same thing. Whereas the compiler would look at the statement and actually generate beta programs that would do a load and an add and a, so forth and so on. And then once that translation happened once at compile time, thereafter the machine would simply just execute the beta instructions. Okay, so we always have this choice about what we do at compile time and what we do at runtime. And we often, when we want efficiency, we want to do as much as we can at compile time, because that happens once, and then when my program runs, I don't have to redo it. Whereas interpretation often gets me to execution a little bit more quickly, but the execution itself is slower. Okay. Okay, so we're going to talk about sort of our first steps is just simply taking that symbolic representation of assembly language programs and thinking about how to actually have them write something called an assembler that takes an assembly language program and produces the binary representation of the instructions in memory. That's going to be pretty straightforward. And then towards the end of lecture, we'll start talking about the process of taking a high-level language like C and translating that into assembly language, which can then be translated into the binary representation. And then on top of that, we will, later in the course, talk about different sorts of interpreters, and the one that we'll actually spend a lot of time on is the operating system. So we'll come back to that.